Let's talk about time dilation. The formula on your screen is the formula for time dilation. This formula looks complicated, so let's explain this using this scenario. Let's say there are twin brothers. Both of them dream of becoming astronauts. Together with their other friend, they all pursue their dreams. But only one of them became an astronaut. The other brother became a mathematics teacher. The brother who's an astronaut went on a deep space mission that is traveling at 95% the speed of light. After 10 years in space, according to the astronaut's clock, he went back to visit his brother who's earthbound. But to his surprise, his brother aged a lot. He aged 32 years compared to his 10 years. What explains this paradox? The answer is time dilation. So when we apply the time dilation formula to this twin brother's case, the computation goes this way. The time as experienced by the astronaut using his clock in his inertial frame of reference is 10 years, but the time as observed by his brother who's earthbound is computed as 10 over 1 minus 95% of the speed of light squared. And performing this computation, you will get a value of approximately 32 years. That is why the brother aged 32 years compared to the 10 years for the astronaut. Our goal in this lesson is to derive this formula. And derivation is different than computation. Derivation requires higher order thinking skills because what you are going to do is to prove that the formula is correct, whereas computation is a mere application of whatever formula is arrived at. In order to derive the formula, let's have these two scenarios. In the first scenario, we have this light clock. A light clock is a clock that measures time by bouncing back and forth a light ray. This part is a mirror and this is another mirror. And these two mirrors are parallel with each other. And we bounce back this light. But we know that light has a constant speed and that constant speed is denoted by c. By bouncing back and forth this light ray, then we'll be able to come up with a ticking clock that measures the time. And in this first scenario, we are in the same inertial frame as the light clock. When we move, the clock moves with us. And for our notation, we use the notation delta t sub 0 to denote the proper time. Proper time is the time measured when you are in the same inertial frame. And the distance between the two mirrors is denoted by the variable d. Some idea about inertial frame. We know that planet Earth is moving around the sun. But despite that movement of the Earth around the sun, it seems that we are not experiencing any movement at all because we are moving at the same speed as the planet Earth. So we are in the same inertial frame. Also, in the computation of the speed of light as 299,792,458 meters per second, this second is defined as 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. So in the atomic clock, time is measured as the number of radiation of this element, which is found to be more stable. Now, let's remember that speed is equal to distance over time. So equivalently, we can solve for time as distance over speed. And by using now this formula for time, we can measure proper time as the distance the light travels back and forth. That means one going up and one going down. So the distance traveled is 2d divided by the speed by which the light is traveling, and that speed is the speed of light denoted by letter c. This is now our formula for the proper time in our first scenario. The proper time is 2d divided by c. So I want you to remember this because we are going back to this formula later on. Let's go to the second scenario. In the second scenario, imagine that you have a spaceship that is moving horizontally and the observer is outside the inertial frame, meaning the clock is outside the observer's frame of reference. The light clock is moving with a velocity of u meter per second in the x direction. So the movement is going this way. A good analogy of this is, let's say there's a wind going this way and you throw, let's say, a piece of paper upward. Notice that because of the wind, the paper will be forced towards this way and it will not fall at the same location where it was thrown up. So that is the scenario here. You have a light, and since the object is moving from the vantage point of somebody that's outside that frame of reference, the light is traveling like this. And the speed by which that object is traveling this way is given to be u meters per second. And for our notation, the time it takes to travel going up and going down here is denoted by delta t. The question now is, how do we compute for the length of L in this case? Notice that what we have here is a right triangle. And in this right triangle, the length of one side of the right triangle has a length of d, and the other is this length. But what is this length? Remember that distance is equal to the rate times the time. And our time is delta t. But remember that delta t is the time for us to move up and down to complete one tick. So therefore, our time should be delta t divided by 2. Because from here going here, that is only 1/2 one tick, because one tick is considered as going up and going down. So our time is delta t over 2. And what is our rate? Our rate is given to be u meter per second. So the rate is u meter per second. Therefore, this length here now is u times delta t over 2. Now, don't think of delta t as two variables. This is one variable, the change in time from here going to this point. So applying now the Pythagorean formula, remember that the Pythagorean formula is c squared equals a squared plus b squared, which is equivalent to c equals the square root of a squared plus b squared. So applying now this formula, our c is this L, that's the hypotenuse. So c equals the square root, so you have this square root. Now, it doesn't matter whether this is a or this is b or vice versa. By commutative property of addition, you can interchange the value of a and b. So if we let d be our a, then our a squared becomes d squared. So we have this d squared plus our b is u delta t over 2 squared. So our b is u delta t over 2. Then we raise that to the second power. So this is now therefore our expression for the length of this line segment L. So we have the formula for the length of this L, and for the time, similar to the way we compute our scenario 1, the time for our clock to travel up and down is delta t, but that is equal to distance over speed. And the distance the light ray traveled is one going up, which is L, and another going down, which is another L. So together we have two L's, that's why you have 2L here. And the speed by which the light travels is the speed of light, which is c. So this is the time for the light ray to complete one tick, but this L here in the numerator is equivalent to this expression, the square root of d squared plus u delta t over 2, all raised to the second power. So comparing now the two scenarios, one scenario wherein the observer is in the same inertial frame of reference, and the other is where the observer is outside the clock's frame of reference. This is now what we have. The time as experienced by a stationary object with the observer at the same inertial reference as the clock is proper time equals the distance going up and down, which is 2d, divided by the speed, because time is distance over speed. Whereas for the second scenario, where the observer is outside the clock's frame of reference, the distance is this L and L, which is 2L, divided by the speed of light. The main difference here is the length of d. D is this length, whereas in the second one, our distance is the L, which is obviously longer. And since the distance here is longer, then we will say that whatever time we compute here is bigger than the time that we are going to compute in the first scenario. We now say that there is a dilation of the time, or the time is expanded in the second scenario. That's why we call this as the time dilation. So as we continue our discussion and derive the formula for time dilation, what we are going to do is we are going to synchronize these two formula. So let's do that. Let's focus on this second scenario. So we have this given delta t, or the time experienced by an observer outside the frame of reference. We have delta t equals 2L over c. But we know that this L here is this L. What we can do therefore is we can substitute this expression to the value of L in this formula. So let's do that. So from delta t, we have this delta t, then this 2 is this 2. This L is now replaced by this. So notice that this part is our L, which is this one, and then you have over C, so you have over C. In other words, we just substitute the value of L to this red equation. So let's erase now these two formula below, and let's concentrate on this formula above. Now, let's solve this equation for D. And remember that the formula for proper time is proper time equals 2d over c. And from that formula, we can solve for d. So we can multiply both sides by c to get c delta t sub 0 and then divide by 2 both sides, and we'll get this expression for d. Let's concentrate on this formula for d. Since the value of d is this formula, we can now substitute this value to this d here. Replace that d with c delta t sub 0 over 2. So this formula at the top becomes this formula. So I copy delta t equals copy 2 square root. When we encounter the variable d, we use c delta t sub 0 over 2. That's why you have c delta t sub 0 over 2. And then you have exponent 2 here, so you have exponent 2. All the rest are copied, plus this expression all over c. Let's concentrate now on this formula. What are we going to do to simplify this? This 2 is not the square root, it's a factor. Notice that you have here a square root. In order to eliminate the square root, what we can do is we are going to square both sides of the equation. We are going to square this, and we are going to square this part. And by squaring that, this is what we'll get. You have delta t squared. This 2 is raised to the second power, so you have 4. And then when you raise this expression under the radical symbol to the second power, the square root and the exponent 2 are cancelled. So we are left with this expression inside the radicand. And then c is raised to the second power. And then we can gather this 4 over c squared as one fraction that we can distribute to the binomial term inside the grouping symbol. So this is what we'll get. And then let's distribute this to these two terms. Now, when we distribute, notice that you have an exponent 2 here. So you'll have c to the second power. And that c to the second power will be cancelled by this c to the second power, which is in the denominator here. So that will cancel the c squared. And then this 2 raised to the second power is 4. And you have 4 here in the numerator, so we'll be able to cancel the 4 and the 4 here. What is left is this expression, delta t sub 0, raised to the second power. That's why we have this part. If we distribute this again to the other side, notice that you have 2 raised to the second power here, and that will cancel out this 4. And so what you have is u raised to the second power, delta t raised to the second power, and this c squared that's left. This is exponent. Let's continue. Notice now that you have here delta t squared, and you have delta t squared here, whereas this one is delta t sub 0 squared. So this is a different variable than delta t here. What we can do is gather all those terms with the same variable, and we call them as like terms. This is what we'll get. We subtract this expression from both sides of the equality to arrive at this part. This is c to the second power. Now, notice that we have here a common factor, delta t squared and delta t squared here. We can factor out that common factor. And so factoring out delta t squared, we have delta t squared times delta t squared divided by delta t squared is 1. This expression divided by delta t squared will result to u squared over c squared equals delta t sub 0 squared. And then solving now for delta t squared, we now have this expression over this factor, 1 minus u squared over c squared. Now, notice that this still raised to the second power. What we can do is we can get the square root of both sides of the equality, and what we will get is we'll be able to cancel this out to get delta t, and then the square root of delta t sub 0 raised to the second power is delta t sub 0, and we have the radical at the denominator. And finally, we now have this formula. So we now have this time dilation formula, which says that the time as observed by someone who is outside the clock's inertial frame of reference is equal to the time as observed by somebody who is inside or who is in the same inertial frame of reference as the clock divided by the square root of 1 minus the speed by which that object is traveling raised to the second power over the speed of the light. And do you know that this is the reason why our satellite navigation system is very precise? Do you know that the Global Positioning System, GPS, that most of us now rely on for navigation uses stable atomic clock in satellites and on the ground to provide worldwide position and time determination? A microsecond discrepancy between the satellites and the ground's clock could translate into 300 meters error in position. Imagine if your GPS tells you to exit 300 meters before the correct location. GPS considered the constancy of the speed of light, the equivalence principle, time dilation, gravitational frequency shifts, and other relativistic principles to do its job. Time indeed is that crucial.